Today we're going to talk about ideal gases. So up until now we have studied about thermal expansion of solids and liquids, but we have not mentioned anything about thermal expansion of gases, and there is a very good reason for that. We know the formula for thermal expansion of liquids, that the change in volume is the coefficient times the change in temperature times the initial volume. Now, we cannot use this formula to calculate the change in volume of a gas, since gases take the volume of the container which they are placed. Hence, it is very difficult to talk about a specific volume at a certain temperature. So, we cannot use this given formula for thermal expansion that we used for liquids. Now, what are ideal gases? Well, ideal gases are basically non-existent, but they are used as a model in order for scientists to simplify some calculations. In gases, it is important to know the relationship between temperature, volume, and pressure. And the equation that interrelates these three values is called an equation of state. Now, this equation is very difficult to derive for real gases, but if we talk about ideal gases, this simplifies a lot, and we will see that equation in just a moment. Now, for ideal gases, it is important to note three things. Ideal gases, as I said, are basically a concept that scientists use in order to model the behavior of real gases. Now, an ideal gas is basically a gas at low pressure, or meaning that has low density. Or to be more specific, a gas that has a certain temperature that is not too low, in order for the gas not to liquefy, but also that is not too high. Now, what are these three important things about ideal gases? Well, first of all, ideal gases. The volume of ideal gases is basically solely based on the movement of molecules, meaning that the volume of molecules, or the size of them, compared to the volume of the container, is basically negligible. So the only volume that ideal gases have are due to the movement of molecules. So volume due to movement of molecules. The second thing is that the particles interact with each other and also with the walls of the container by elastic collisions, meaning that there is a conservation of momentum and also of kinetic energy. Now, when I say interact, that means that the molecules interact with each other only when they're a small distance apart. But molecules do not affect the movement of each other if the distance between them is large. Meaning that for ideal gases, we can simplify their model and say that they only have kinetic energy. That the molecules have only kinetic energy, since the distance between molecules is so large that the potential energy is negligible compared to the value of kinetic energy. Okay, so these are the three important things about ideal gases, and real gases act like ideal gases, as I said, at low pressures. Now, what is the formula of an ideal gas that interrelates those three quantities that we saw a few minutes ago? Now, the pressure times the volume is equal to the number of moles times the universal gas constant times the temperature. Now this is the ideal gas formula. P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. Now, as we can see, pressure and volume are inversely proportional, meaning that when the pressure is increased, the volume is decreased. Now, the pressure and the temperature are proportional, meaning that when the pressure increases, the temperature increases, and when the pressure decreases, the temperature decreases. The same thing is between volume and temperature. When the volume increases, the temperature increases. When the volume decreases, the temperature decreases. Okay, now we can interpret this formula. Now, the universal gas constant was found by performing a few experiments, and they found that when the pressure was dropped to 0 pascals, that the value of the value of V over N times T was dropped. When the pressure was dropped, that this value was 8.314. Now, the units of the universal gas constant are 8.314 joules over mole times Kelvin. The temperature, as we discussed in an earlier video, is measured in Kelvin. Now we can interpret this formula as I said. For instance, instead of the number of moles here, for N we can write the number of molecules over Avogadro's number. So here in the formula we'll get P times V is equal to N over Avogadro's number times the universal gas constant times temperature. Now R over Na is equal to the Boltzmann constant. That's equal to 1.31 times 10 to the power of negative 23, and it's expressed in joules over Kelvin. Now that's about it. Also here, instead of writing N like number of moles, we can write, since N is equal to, let's see, the mass of the gas over the molar mass, we can write that in the formula. Now the molar mass of a gas is equal to its atomic mass, only the units are grams over mole. For instance, for carbon, the atomic mass is 12 units, but also the molar mass is 12 grams over mole. Now in the next video, or in the next several videos, we're going to solve some problems using the ideal gas law, and then we're going to move further on into the world of thermodynamics.